All right, today we're cracking open a brand new case file. But this time, the crime scene, well, it's inside your own bloodstream. The victims are millions upon millions of your red blood cells. We're going to be investigating hemolytic anemia, a condition where these absolutely vital cells are being destroyed way too early, and our job is to figure out why. So, what actually happens when the very cells that are supposed to carry life-giving oxygen all over your body get taken out faster than they can be replaced? I mean, this isn't just a medical condition, it's a high-stakes internal conflict. So let's start where any good investigation does, by examining the evidence. At its core, the definition is pretty simple. Hemolytic anemia is all about imbalance. You see, the body's red blood cell factory, that's your bone marrow, is working overtime, churning out new cells as fast as it can, but it just can't keep up with the sheer rate of destruction. And this fundamental imbalance is right at the heart of our entire investigation. Every investigation has to start at the beginning. So our first stop is understanding the crime itself, the premature death of a red blood cell. What does that actually look like on a biological level?
So, under normal, healthy circumstances, a red blood cell lives for a pretty long time, about 120 days. And during that time, it's just tirelessly delivering oxygen. This is our baseline. This is what's supposed to happen. In a healthy body, this is the natural order of things.
And here is where our crime begins, hemolysis. That's the technical term for when that 120-day lifespan gets cut short, sometimes dramatically short. The cell is destroyed way before its time. This is the inciting incident, the event that kicks off our entire investigation. Now, when a crime happens, it always leaves behind evidence, and inside the body, that evidence is biochemical. By following this trail of molecules and byproducts, we can really start to understand the wide-ranging consequences of all this destruction. Okay, so let's follow the clues. When a red blood cell bursts open, its most important passenger, hemoglobin, spills out. The body immediately goes into cleanup mode. The globin part, that's the easy part. It gets efficiently recycled into amino acids. But the heme part is a bit more complicated. Its valuable iron gets sent right back to the bone marrow to make new cells, which is great, but it also creates a waste product called bilirubin. So what happens when you have this massive, widespread hemolysis going on? Well, the body gets flooded with that bilirubin waste product faster than the liver can possibly process it. And this is the direct link between that tiny microscopic event and the physical symptoms a person might actually see. This excess bilirubin is what causes that classic yellowing of the skin and eyes, which we call jaundice, and it can also make your urine appear much darker. But what about all that hemoglobin that spills right into the bloodstream? Well, the body has a few specialized cleanup crews for that. First up is a protein called haptoglobin. Think of it like a sponge. It just soaks up the free hemoglobin. When hemolysis gets really bad, the haptoglobin levels in the blood just plummet. That's a huge clue for doctors. Any leftover hemoglobin gets filtered out by the kidneys, sometimes even showing up in the urine, while another protein, albumin, pitches in to help clean up the rest. All right, time for the next phase of our investigation, profiling the suspects. See, every crime has a cause, a culprit. And in hemolytic anemia, we can basically sort all the potential causes into two main categories. The big question is, was it an inside job, a flaw within the red blood cell itself? Or was it an outside force, some kind of external attacker? And here you can see the two main profiles side by side. On the one hand, you've got the inside job. The technical term is an intracorpuscular defect. This basically means the red blood cell was faulty from the very beginning, destined to fail because of some internal flaw. This is almost always something hereditary, like sickle cell disease. Then, on the other side, you've got the outside force, an extracorpuscular cause. Here you have a perfectly healthy red blood cell that gets attacked and destroyed by something else, like antibodies in an autoimmune disease. These causes are typically acquired later in life. Now, you know in medicine, there's always an exception to the rule, right? Well, this is a classic one. A condition called paroxysmal nocturnal hemoglobinuria, or PNH for short. It's a defect within the red blood cell, so it's an inside job, but it isn't hereditary. It's actually caused by a mutation that's acquired during a person's lifetime. It's a key little detail, a real curveball that doctors always have to keep in the back of their minds. So we've identified the crime and we've profiled the main suspects. But now, how does the system as a whole react to all this? When red blood cells are being destroyed on this massive scale, the body sends out some very clear distress signals, and these are the clues that investigators are looking for.
So the first major clue is the body's panicked response. When it senses this huge loss of red blood cells, the bone marrow basically hits the emergency button and goes into overdrive. It starts pumping out these young, immature red blood cells called reticulocytes at an incredible rate. A high reticulocyte count, we're talking over 2% of the total red cells, is the single biggest, most important hallmark of hemolytic anemia. It's the body practically screaming that it's trying to compensate for a massive loss. But beyond that reticulocyte count, investigators find other important clues. For instance, LDH is an enzyme that's packed inside red blood cells. So when they break, LDH levels in the blood shoot way up. And very often, the spleen, which acts as the body's filter for old and damaged blood cells, gets completely overworked and starts to enlarge, a condition we call splenomegaly.
In any investigation, where the crime happened is crucial, and it's the same here. The location of the red blood cell destruction leaves very different patterns of evidence. If the crime scene is intravascular, meaning inside the blood vessels, you'll find direct evidence like hemoglobin in the blood and urine, and those haptoglobin levels will be rock bottom. But if it's extravascular, happening mostly in the spleen and liver, the evidence looks different. You're more likely to see things like an enlarged spleen, as the organ works overtime to filter out all those damaged cells.
And finally, we get to the resolution. How do doctors take all of these clues, all of this evidence, and definitively solve the case? Well, they use a specific set of diagnostic tools to confirm that hemolysis is happening and to pinpoint the exact cause. This is where the real-life CSI work comes in. Looking at a blood smear under a microscope can reveal the telltale shapes of damaged cells. The direct Coombs test is like a forensic analysis. It's looking for the fingerprints of antibodies stuck to the red blood cells. And finally, testing for bilirubin, haptoglobin, and LDH, that confirms all the biochemical evidence we've been tracking, and it really helps put all the pieces of this complex puzzle together. And that really brings us to our final thought. You see, identifying that hemolysis is happening is just the first step. With a list of suspects ranging from tiny genetic flaws to a full-blown autoimmune attack, the true art and science of medicine is in uncovering the unique origin story for each and every patient. Because only then can you figure out the right way to respond. Thanks for joining me on this investigation. All right,